Hi, this is second part of relations and directed graphs. So before start, we're going to review last class. So what is relation? Relation is kind of some connection, some operation between two things, and so we have uh, two sets, and there is a relation between those two. So this is kind of binary relation from A to B, and so we can make a pair of each element to generate relation. So in this case, we can use this Cartesian product here. So there will be a pair A and B. So this is kind of relation. And if you have a single set, we can do similar thing, but in this case, A1 to A2 or same element A to A. So we have seen many relation. I said about the operation. The binary operation is simple example, and we can use this kind of thing, greater than equal, less equal, or subset. They are all relation. And here is another example. The relation one is about set ABC, another set 1 to 3. So we can make this A to 1, B to 1, A to 2, and B to 3, C to 3. Their relation in this, and we have two set ABC and 1 to 3. And second one is some relation with this modular operation. So in this case, we can get this congruence between x and y, and it is based on modular 5. So those two have same remainder. So that can give you a relation. So third one is about two specific thing. C1 is a prerequisite of C2, so it is just one directional relation C1 to C2. And last one also similar. Student S have taken course C. So yeah, and there are four different properties of relations. If we have a relation R on set A, first one, reflexive is about A to A. This relation goes to itself. Or symmetric, if you have a relation A to B, B to A is also available. Antisymmetric is opposite of that. If you have AB, um, B to A is not available. The last one is transitive. If you have A to B and B to C, there is A to C as well. So it has some connection inside of the relation. Okay, so so um, so which relation have which properties? So this greater than equal on, and it has reflexive because of the equal sign, anti-symmetric because of greater. Yeah, if you change the order, it's totally different. But it is transitive because if you have 1, 2, 3, one is greater than one is 2 is greater than 1, 3 is greater than 2, 3 is greater than 1 as well. Yeah, that's why. And other things are similar, but this one doesn't have reflexive because it doesn't have equal sign. Equal is reflexive, definitely. That's why it is symmetric and transitive. The subset is similar to the greater than equal, and modular for the congruence. This one also has reflexive because maybe if you have same number that has same remainder. And symmetric, yeah, is available. This is like equal sign, and transitive also available. The last one is a single rule, C to C1, C1 to C2, from C1 to C2. That means always one direction. This is antisymmetric, and I don't know, there will be other properties because you have single rule, single relation. It doesn't have any other element, and so that's why it is not available. So when you have two relation, we can connect them together if there is common element. So here we have R. This is A from A to B. R is B to C. So if you combine them together with composition, we can say this S circle R. So in this case, we can apply R first, then apply S. So that's why we have this S. R will be AB, S is BC. So that means it will be AC. So you can simply say it is S of R, and maybe there will be another, but this can make connection with a common element. So here are examples. So we have parent relation and sister relation, and sister circle parent, which means sister of parent. We know that is aunt. So A is an aunt of X. So next one is different order, parent circle sister. What I said, we can simply say this parent of sister. So that is parent again. So Y is the parent of X. So yeah, we can do opposite way. If you have a specific relation, we can make a combination using these relations. So uncle, yeah, uncle is a brother or parent. So we can say brother circle parent. Cousin is a little bit complex. It has three relations to describe this. So this is child of sibling of parents. So that's why child circle sibling circle parent. So we can combine them together. It is same to cousin. Okay. Yeah, we can use this kind of rule with powers of relation. So previously we have combined two relation into one. In this case, we can use a single relation to make another. 2 square, r square is about r circle r. That means there will be AB in R and another relation BC also in R. We can make AC using it. And to the zeros, that is another relation. Actually, we have R, but it is about equality relation on A. So any element in A, that will be small a, we can say this pair of small a and another small a. So this is about equality. And if you have one, yeah, that is it's just the same to original relation R. If you have multiple R, that means you can combine R and again. So here, maybe this is R square circle R, that is again R cubic. And so we have seen this pair, the Risto pair, to describe this relation. We can also use matrix, because matrix has two parts, row and column. So row will be starting point and column will be end point. We can make a pair with this. So 1 to 1 is here. There is the relation. We can put 1. If there is no relation, there is nothing between those two, we can put 0 like here. So we can rewrite this Risto pair into a matrix. And because of that, we can use graph as well. So graph is about vertex and edge. Vertex is node, which is the element. Edge is the connection between two vertices. So we can make this kind of relation with this one vertex to another vertex with directed graph. And there is some path which is related multiple at node or vertex. So we can make this kind of relation with this path. This is actually from here to there, but we can go with goes through this multiple node to be there. And there are several types of paths. So there are simple paths. It doesn't have any repetition. So this is about path from one node to another node, one vertex to another vertex, and there is no repetition in that. So that's why this is simple path. If you have some repetition, we can call that is cycle. Actually, cycle means vertex 0 and vertex k are same. That means so the starting point and end point is the same. So we can say this is cycle. Okay, we can also say this is cycle, because there is two thing and starting point and end point. If they are same, it doesn't matter there is any repetition of the vertex digit. So, but if you have a single, if you have a simple cycle that doesn't have some repetition inside of that, so it only has a repetition on starting and end, and between those inside of this path there's no repetition like simple path. So it starts from here, goes this way, come back to the original place, but it doesn't have other repetition. That's why this is simple cycle. And so here is the directed graph, simply digraph. We have the original representation of list of pairs. We can simply write down this edge in this node. So we can put AB and AA, BA, CA, CD, CE, and last one is DE. So we can simply represent the relation in this graph, and we can also use the composition operation on this graph. So here we have two relations S and R. So we want to compute S circle R. So we have this graph. The relation S is orange color, relation R is a purple color. So we want to combine them together. So first we need to start from R, 1, 2, and next we can follow this orange line here first. That is this relation, and another one is here, so that means this relation. Yeah, that's it. And next one, so this can do here, and again this, so that means this. So another one here, we have 2 and going to this place, but there is no orange line, we cannot go further, so we cannot use this. And 3 doesn't have a purple line, we cannot make this combination, and this is the answer. Okay.